Okay, folks, welcome back to another episode of Physics 361. And today, it's going to be mostly a recap video. I want to sort of break it up a little bit and look at the Drude model again and recap what we've already learned about the Drude model. Okay, so let me share my screen here with you. Okay, so let's do a recap here. We have basically in the Drude model these valence electrons that become basically the free electrons, and they can be pictured as little marbles that are constantly colliding with the lattice ions. They're colliding ballistically. Okay, they're basically bouncing off, and every time there is a collision, these electrons, in a sense, sample the temperature of the lattice. They get a kick that is consistent with the temperature of the lattice at that point. Okay, and in addition to that, there's also an electric field that accelerates these electrons. Why is there an electric field? Well, it's an applied field that comes from an applied voltage. Usually we apply a voltage across a metal, and so there's going to be that accelerating field. That's the idea, and so we get basically this equation here. We get a force that comes in two parts. There is the E times capital E, that's the force from an electric field, right, that the electrons feel. And then there is this gamma times V minus gamma times V, which is the effective damping force. That damping force comes about due to the myriad collisions that the electrons undergo with the lattice ion. So it's sort of an effective result, an effective result that arises from a trillion little interactions. So that's how we model it simply and mathematically tractably. We just throw in this damping term, okay? But the physical origin is the many collisions that we get. So we have to remember also that gamma here is the damping coefficient, but it can actually be related to tau, the relaxation time, right? That relaxation time is basically the average time between successive collisions that an electron would undergo. And so we can cast the gamma in terms of the tau, and you see that the two are inversely related. Gamma is equal to m over tau. And so that kind of makes sense as well, because if you have a long time in between successive collisions, well, then there isn't a whole lot of damping going on. And so it makes sense that the two would be inversely related. Okay, so let me let me show you this little demo. You might have seen it in intro physics, but there's no harm in looking at it one more time. Okay, so here it goes. Let me switch perspectives. Okay, so we come over here now. Okay, and you've seen this before. We have this inclined plane, and I can take a marble here, actually a ball bearing here, and let it go down the inclined plane. Normally, it would just accelerate down due to gravity, pick up speed along the way. But you may be able to see here, this is not just an inclined plane. What we also see are these pegs everywhere, right? These pegs are in the path. And once I take a whole bunch of these ball bearings, which are supposed to represent the electrons, okay, this here is my wire, and the pegs here are supposed to represent the ions. Okay, so if I take a whole bunch of these electrons and let them and launch them down this incline, then what you'll hopefully see is that we get some kind of drift velocity out of this. So let me do that. Okay, And so I don't know if you were able to see that very well, but it did seem to me anyway that these electrons were sort of eventually going down this inclined plane at a constant rate, at a constant speed. Yes, they get accelerated by gravity, but they get damped by the collision with these pegs. So let's look at this one more time. We'll grab a couple more. Okay, here we go. And yes, it does seem like a constant drift velocity down this inclined plane. Now, we could do a couple of more runs here, and what I could also vary is the incline, the angle of incline here. I could raise this up, make this steeper, and in that case then we would see that the drift velocity would be higher, and that kind of makes sense. So the drift velocity is dependent on the electric field we saw. And here, of course, the electric field is being replaced, or is being played by gravity, right? And so as I increase the strength of gravity, then I do increase that drift velocity. Alternatively, I could also lower this here, make that incline more shallower, and you'd see a reduction in the drift velocity. Okay. All right. Okay, so that's the basic outline of the model. Now, we can talk about first the strengths or the successes of this model. And first and foremost, the one that we've already encountered is the Wiedemann-Franz law, which relates the electrical conductivity of a particular metal to its thermal conductivity. And it says that the two go hand in hand. If we have a particular metal that is a very good conductor of electricity, and it must also be a good conductor of heat. So that's the Wiedemann-Franz law in a nutshell. Mathematically, we can form this particular ratio here, this ratio of the two conductivities. Here's K, the thermal conductivity. Here's sigma, the electrical conductivity. And then I also throw a factor of 1 over T in there as well, T for temperature. And so this particular combination then is predicted to be a constant, right? So on the right-hand side, you just see constants. Here is the Boltzmann constant here, and then there's the fundamental charge E there. Okay, you square that, and that gives you this constant. So basically, if you're doing these experiments at a fixed temperature, then this capital T is not even really that important. You get that this ratio between the two conductivities is just always the same for all metals. If you are doing the experiment at a different temperature, okay, then you do have to, factor in that 1 over T as well. In any case, that prediction turns out to be quite accurate when you compare it to experimental measurements. Okay, so that's definitely a success of the model. A second success would be optical properties of metals, our next topic, and also the subject of our next video. Okay, so we're going to get there momentarily. So this is how metals interact with light, interact with electromagnetic radiation. And so here we see that the Drude model predicts correctly that metals would be opaque for low frequencies of electromagnetic radiation. So certainly in infrared, radio frequency, infrared, okay, and into the visible, we know that metals are opaque. They're not transparent. I can't make a window out of a metal, You can't see through metals, but then at higher frequencies in the UV somewhere, you do start getting some of this transparency. So metals tend to then all of a sudden become transparent to high frequency electromagnetic radiation. And it turns out that the Drude model predicts that and also gives you a pretty good idea of when that crossover might happen in frequency. Okay, so we'll get to that next time. But let's also first look at a couple of failures. So we've already said that it doesn't do very well with predicting the heat capacity of metals, right? Because it gives us a prediction of 3/2 times R, but it turns out that that prediction is way too large. In reality, we have an electronic contribution to the specific heat that is much, much lower than 3/2 R, probably by on the order of 100 times lower. So it doesn't do very well there. Furthermore, it also, as we said before, doesn't really give us, doesn't really predict the differences between monovalent and divalent metals very well. Okay, so it doesn't give us the complete picture there, and is actually misleading here. And an example would be, for instance, beryllium, which is a divalent metal, every atom contributing 2 electrons, 2 conduction electrons. It has a small ionic radius, so the ions are packed pretty close together. Those two together then gives us a very large number density for conduction electrons. It's one of the highest ever. It's 25 times 10 to the 22nd conduction electrons per cubic centimeter. So that's a very large number. Okay, and if you compare that to copper, which is a monovalent metal, there we get a number density of charge carriers that's much less. It's only about 8.5 times 10 to the 22nd per cubic centimeter. Okay, so if you now go by the Drude model, then you have to conclude from these numbers that beryllium would be a much better conductor. After all, electricity is conducted by the motion, via the motion of its charge carriers. That's what electricity is, right? It's the motion of charge carriers, and if you have more charge carriers, then there should be a greater current, and it should be a better conductor. There's really no way around that. There's no way to finagle that, okay? And so that's just what the Drude model would predict, but that's just not what we're seeing, right? Copper has a conductivity of about 60 mega Siemens per meter, and beryllium is down at 25, so it's less than half of it. And so that is a discrepancy that the Drude model just cannot explain, and I would call that a failure. Okay, we'll come back to this point here and try to see why that is, why why copper is nonetheless such a good conductor compared to beryllium. And so we have to then shift into the quantum mechanical picture if we want to understand that. All right, another failure has to do with the thermoelectric effect. Okay, so what is the thermoelectric effect? Well, in a nutshell is if I have here a metallic wire or a metallic bar, and I start heating up one end here, maybe the left end, and I cool down the other end, the right end of that bar, then what I get is a net flow of electrons from hot to cold. Okay, so this is not in response to a voltage that I apply. There is no voltage applied here at all. All I'm doing is I'm creating this temperature gradient between the two ends of this metallic wire or bar. Okay, that's all I'm doing. So why would there be then a flow of electrons? Well, we said that it's just a thermal phenomenon, right? So like these electrons over here collide sort of more violently with the ionic lattice. Okay, and so they will get scattered at an average higher velocity than electrons over here. Okay, so there's electrons that get scattered in all directions. Some of them will be scattered to the left. And on average, they have these electrons, a subset of electrons that get scattered to the left would have a larger speed than electrons over here that start out on the right that happen to be scattered to the left. And so we see that then the net effect of all of that is that electrons will drift from left to right, okay, until, of course, a new equilibrium is established, okay, because this can't go on indefinitely. You know, as we get sort of a slight imbalance in electrons, then an electric field develops that discourages further electrons from migrating to the right. There's already some electrons accumulating on the right, and that then discourages further electrons because like charges repel. And so eventually then, or very quickly, an equilibrium is established, okay, but that equilibrium has a charge separation, a static now charge separation. And so once you have a static charge separation, you also get a voltage delta V, or simply just V, okay, and that voltage can be measured, okay, with a multimeter, okay, probes on either side, and you will see that you'll not be surprised here that that voltage that I measure would be proportional to the temperature difference. After all, the temperature difference, delta T, is the cause for that voltage. Okay. So the thing, though, is that the Drude model predicts an S. Okay, that's the constant of proportionality, sometimes called the Seebeck constant, or the thermoelectric power. That constant is predicted to be about 100 times too large compared to what we measure. So a factor of 100 is, I would say, quite severe, okay? We're just way off. And that counts as another failure of the Drude model. So the upshot is, in general, there's lots of issues with this particular way of viewing electrons in a metal. Okay, there's lots of issues. It's not a accurate reflection of reality. It's just not reality, but maybe then again, maybe that's too high of a bar for any model to strive for. But here we're just quite a bit off from reality. Nonetheless, the model can be quite useful and also quite beneficial in providing us with a mental picture, a conceptual picture that we can visualize. And that picture is sometimes useful to adopt. Now, as long as we don't take it too seriously and start claiming that it is an accurate depiction of reality, so as long as we don't go into that extreme position or that extreme view, and we treat it a bit more lightly, then there's really no problem with using it, because sometimes it is actually quite useful to picture the situation such, okay? So I would say one of the one of the strengths and one of the useful areas for the Drude model has to do with optical properties of metals. It just gets that bit of it right. And so that then justifies, for us, at least in that context, it justifies really taking this Drude model, you know, as a useful model for us to picture. Okay, again, so that's that kind of tension you see in science more generally, if I may drift into philosophy of science just a bit. You see that tension between models on the one hand and reality on the other hand. We see that quite often, right? And quantum mechanics warns us about taking any model too seriously, right? It sort of yanks that conceptual layer out from under us. Nonetheless, oftentimes it is very useful for us to develop models, conceptual models, also models that allow us to visualize what's happening. Yeah, that is still a very useful exercise, even as we at the same time acknowledge that such a model cannot ever capture the totality of the real system. Okay, so next time, optical properties of metals. Stay tuned, folks. More on that in a little bit.